In this video, we're going to talk about graphs and their representations in programming. So we've already seen some examples of graphs so far. We discussed the general idea of graphs, and then we saw how trees generally are going to work in programming. And now we need to discuss a little bit about more of the general graph, which, as a reminder, let me just change the color here so it's more visible to see. As a reminder, we have a bunch of different nodes, and we have a bunch of different edges between those nodes, right? Those edges may be directed or undirected. Directed meaning that they move in one direction. So in this example here, if we had a directed edge, it would mean that we could move from A to B, but not from B to A. Or they could be undirected, which means that we move in both directions. So in this case, A moves to C and C moves to A, right? Now the question is, how can we represent this? We saw with a tree, it was pretty easy to create a representation of my different nodes and their edges, because generally all of the trees that we discussed were binary, meaning that there were only two possible options. We had a left and a right, so it made a really clean sort of node object where we had a value, a left and a right, and we were set. But with graphs, things get a bit more complicated, right? Graphs could have references to themselves for edges. They could have multiple edges to the same node. They could have infinitely many edges between many different nodes. So being able to represent this as a node object becomes a bit more complicated. But we have two different approaches that work pretty well for the representation that we use throughout this section when we deal with graphs. Let me draw you out a graph here, and we'll use it as our example graph. We'll just do a nice simple graph like this. There are two different approaches that we'll typically use to represent a graph. The first would be what we would call an adjacency list. And the idea of an adjacency list is that it represents adjacencies between nodes. Now, we haven't really formally discussed an adjacency yet. Two nodes are considered to be adjacent if they have an edge between them. So in this example here, A and B are adjacent to each other because there's an edge that connects A and B together. When we take a look at directed graphs, the definition changes slightly. Two nodes are seen to be adjacent if there is an edge that connects them in the direction, right? So A is adjacent to B, but B is not adjacent to A because there is no edge that goes from B to A, but there's an edge that goes from A to B. And that's the definition that we'll generally use here for adjacency. The idea of an adjacency list is that we create a list entry for each of the different nodes that we have. And inside of this, we have a list of the nodes that are adjacent to it. So in this example, A is adjacent to B. It's also adjacent to C. We see that B is adjacent to A, and it's adjacent to C. We can see that C is going to be adjacent to A, and it's adjacent to B. So that's the way that our adjacency list works. With this sort of approach, anytime that I want to find out what's adjacent to a particular node, I just go to its entry inside of my list, and it will give me everything that's adjacent to it. Usually, I like to represent this as a dictionary, where these nodes are the keys in the dictionary, and then these nodes are the values in the dictionary. That way, if I want to find a particular value, I just look it up in the dictionary, and I get all of its adjacencies listed out. So this is one of the representations that we will commonly use. The second representation that you may see commonly is what we would call an adjacency matrix. In an adjacency matrix, we use a matrix to represent the adjacencies of our nodes. So generally what we'll do is we'll list out the rows and the columns to represent all of the nodes inside of our graph. And what we'll say is that there is a 1 where two nodes are adjacent and a 0 otherwise. So A isn't adjacent to itself. There's no edge that leads from A to A. But there is one that leads from A to B and one that leads from A to C. Similarly, there is an edge that leads from B to A. There's none that leads from B to itself, but there's one that goes from B to C. And then right here, we can see that there's one that goes from C to A, from C to B, and there's none from C to C. So this would be our adjacency matrix. Now, if we have a graph that has multiple edges, we can modify this to say that this would be the number of edges between a node. So in this case, there's one edge. If there were two edges, we could make this 2, right? So we could modify it simply in that way if we wanted to. There's a lot of interesting properties that come from adjacency matrices. You'll see here, for instance, that because this graph is connected, we see that there's actually symmetry in it. Along this triangle here, right, this lower half is the same as this upper half. So we actually see some symmetry inside of this matrix. There's a lot of really interesting properties. I'm not going to go too in depth of the different properties that exist unless we're using them in a particular algorithm. If you're interested more in that, you can take a look at graph theory or discrete math, which will go into a lot of those kind of details and theorems. For now, I just want to give you that idea that these two representations generally exist. When we work with a graph, the very first thing that we do is we say, which of these representations are we going to use? And then we go ahead and start using it as optimally as possible to be able to solve our problems. So with this solid foundation, we'll now be able to move on to talking about graphs and their various algorithms. So thanks so much for watching. I'll see you in the next video.